So we're going to continue talking about noise today, but before we get on this new set of notes, I want to address something that Pierce brought to my attention the other day, because we're going to be doing it a lot, so it might be a little bit confusing. So if we have a noise voltage source, so that we have some resistor R in series with some noise voltage source Vn squared like so. I said anyway, that we could represent this as a noise current source in parallel that same resistance R, where on the left hand side here Vn squared was 4 kBT R, and on the right hand side here In squared is 4 kBT over R. And the question that Pierce asked was effectively, how do we get from one to the other, because it's not intuitively obvious, right? And so what I mean by that is the units here for our noise voltage is volt squared per hertz, and the units here are going to be amp squared hertz. So if we were trying to employ traditional Thevenin and Norton equivalent circuit techniques, we could say that this open circuit voltage here should be exactly equal to Vn squared, right? Well, we get that by saying that it's going to be In squared times R, resistance, squared, okay? So instead of just converting by using the resistance, we have to square it. And it goes back to that statement that I had made earlier about the input transfer function, or excuse me, the input noise spectral density multiplied by the square of the transfer function gives us our output spectral density here, right? So the transfer function of this simple network containing a resistor is the resistor value itself. We have to square it to get to that output noise voltage, right? So I wanted to revisit that because Pierce had asked a question about it. I tried explaining it in a complicated way and then thought, oh wait, it's literally nothing but the square of the transfer function. That's probably much easier to understand. So I thought I'd bring it to you all's attention. And we're going to be using that relationship extensively, so I thought it was important. All right. So with that taken care of, let's talk about thermal noise in MOSFET. So this is a continuation of our discussion of thermal noise. All right. So as I believe I mentioned at the end of our last class meeting, MOSFET transistors also exhibit thermal noise, with the most significant source being what's called channel noise, which is caused by electron fluctuations during the inversion process, okay? So let's consider a MOSFET transistor operating at the case where VDS is exactly equal to 0 volts, right? So at VDS is equal to 0 volts, we had a transistor, something like this. Here is our see if this is going to be an NMOS. So this is N plus. This is N plus. We have a thin gate oxide. Then we have a polysilicon layer up here. And let's just say for the sake of argument that our source voltage is 0 volts. And our drain voltage is 0 volts. And our gate voltage, VGS, is greater than or equal to VT, such that our transistor is turned on. In this very specific case, where the source and the drain voltage are equal, the channel looks like a homogeneous resistor, right? It's a material that's got a lot of charge carriers taken out of it, right? So free charge carriers taken out of it, so it's left, it's got a space that's left behind with a lot of bound ions. So it looks like a resistance. So let's call this resistance RDS not. Okay, so let me write this slightly better. RDS not. So in this very specific case, we can say that the noise current spectral density would be 4 kBT over RDS naught. All right. So we're treating the transistor as a simple resistor, and then we're going to see what happens when we apply bias voltages, right? So whenever the voltage present at the drain terminal is above the voltage present at the source terminal, what happens to the profile of our inversion layer? Tilts, right? So for VDS, so draw it again real quick here. Here's our N plus. Here's our N plus. Here's our polysilicon layer. Let's leave this source still at 0 volts. Let's say that this VD is greater than 0 volts. And VGS is greater than or equal to VTH. So our transistor is on. We don't particularly know whether or not the device is in saturation region or not, but we know that our profile, actually I can't draw it that exaggerated because that would force it to be in saturation. So it looks something like this, right? So we now have a non-homogeneous resistor. So what we're going to have to do is to evaluate what the power spectral, we're going to break that channel up into small differential elements, determine what the power spectral density is at each of those individual differential elements, and then integrate over the whole thing to figure out how this guy behaves. Okay. So our drain current noise spectral density is going to be 4 kBT times mu n C ox W over L quantity squared multiplied by 1 over our bias drain current ID times the integral from 0 to VDS of VGS minus the voltage at whatever position we are at physically across the channel minus VTH quantity squared dV. So this is similar to the integration that we were doing when we figured out how the drain current and all that kind of stuff worked here, where this bit right here really just represents the charge. It's moving around in our channel, okay? So if we perform this integration, what we're going to wind up getting is 4 kBT UN Cox W over L times 2/3, and then this big ugly guy right here, 3 times VGS minus VTH multiplied by VDS minus 3 VGS minus VTH squared minus VDS squared, and all of this is over twice VGS minus VTH minus VDS. Well, this thing looks terrifying, right? Looks like it's got a whole heck of a lot of stuff going on, but under the specific condition where our transistor is operating in the saturation region, this simplifies to 4 kBT times 2/3 mu n Cox W over L VGS minus VTH, which is nothing more than 4 kBT gamma times the transconductance, where this gamma guy right here represents the transistor parameters and bias conditions and is effectively going to be 2/3 for long channel MOSFETs, which is what we're going to limit our analysis to. Okay, so it comes down to something fairly nice and neat. Okay, so this guy represents our noise in our channel flowing from the drain to the source. So we would model it as part of our transistor model. Here's our gate, here's our drain, down here is our source. And so we're going to put it between our drain and our source like so. So here is our drain current spectral density, 4 kBT gamma. So before we move on, I want to ask you guys something here. What is our basic expectation of this noise? So what I mean by that is, do we expect it to appear in our large signal model? Do we expect it to appear in our small signal model, or both? Any thoughts? Just the small signal model, exactly right, yeah. So the noise isn't going to be enough to cause any, it's not going to push us out of our bias conditions or anything like that, but it is going to be enough to where when we're using transistors as amplifiers and stuff like that, it's going to potentially be a pain in the butt and something that we're going to have to consider, okay? So with that in mind, let's figure out what the maximum noise voltage of a transistor can be, okay? So the maximum output noise occurs when the transistor sees only its own output resistance. So if we had a common source amplifier, like so, and we biased it with some ideal current source I0, such that at a small signal level, the transistor is only loaded by its own internal resistance, we'd have something like this, right? I'm going to call the gate terminal here specifically AC ground. And so what I mean by that is our transistor is biased in such a way that it will be in saturation, but we are shorting out whatever small signal input we have because we want to see only the effects of the noise voltage at the output, right? So for the next little bit, we're going to effectively always assume that our input signal, our true input signal is shorted to ground, so that we're only looking at what happens as a result of the noise. That'll be key in just a moment. So if we took this guy to our small signal model, our gate terminal is at our small signal ground. Our source terminal is also at ground. Here we have our dependent current source. So converting that input signal, which in this case is 0, to current at the output. Here we have our output resistance R out. Here we have our noise generator, right? So it's going to show up between the drain and the source. So this guy is IN squared. And here is where we take VN out. Sorry, do it backwards. All right. So one thing here that I'm going to mention, I have arbitrarily chosen the direction of our noise current to be down. It's a random process and we're going to wind up squaring things anyway. So the direction literally doesn't matter at all. Okay. So I'm going to call my output voltage is always positive because we understand that it's a statistical distribution and it's just as likely to be positive as it is negative and all that kind of good stuff. So effectively, we get to play a little bit fast and loose with signs here. So my output noise voltage, in this case, VN squared out, should just be understanding that this dependent current source is going to provide no current whatsoever because VGS is 0. We're going to see that we have that current, noise current IN squared, flowing through our output resistance squared, right? So this is representing the transfer function of our small signal model for our transistor here. Gives us simply 4 kBT gamma GM R out squared. Now, what's particularly interesting about this is that I set the circuit up as a common source amplifier, but this would be exactly how a common gate amplifier would behave as well, right? Because since we are zero, whenever we're doing any of these noise calculations and all that kind of stuff, we're zeroing out our input signal. So for the common source, our input signal is zeroed out or connected directly to ground, or excuse me, the gate terminal is connected directly to ground. And because of the type of transistor amplifier that we have, the source terminal is also connected to ground. Well, for a common gate amplifier, it's literally the exact same, or it looks like the exact same thing, right? So this is valid for both. Okay, so that's kind of interesting. So what can we say about the noise, or at least the output noise here in this simple one-stage transistor amplifier? Do we have any control over Boltzmann's constant? No. Do we have any control over the temperature? Maybe a little bit, but generally speaking, this thing is going to heat up and be at whatever temperature it needs to be during its operation, right? We have some control over that output resistance, right? In this case, it looks like we would want to make it smaller to eliminate the noise. But if we make the output resistance smaller, how does that affect our transistor's ability to amplify signals? It also gets smaller as well, right? So the smaller we make this, the crappier of an amplifier we have because we're lowering the gain as well. So the only thing that we really have direct control over is our transconductance there, right? So if we want to make our amplifier less noisy, we have to make our transconductance smaller, right? So in addition to the channel noise, the ohmic sections of a MOSFET also contribute some noise. So I'm going to draw a drawing here real quick just to kind of hopefully illustrate what I'm talking about here. So here's our polysilicon region. With a contact right here in the middle. And then we have an active region up here and an active region down here. So this is a pretty basic transistor where this is our gate, this is our drain, and this is our source. Because the polysilicon has some finite resistivity we've talked about previously, that means the gate has some resistance. Because the active regions have some finite resistivity, that means the drain and the source look like resistances as well. Now, what do you guys recall about the resistance of the active regions? The sheet resistance was on that last sheet of your exam that you turned in last week. Anybody remember anything about it? How did it size compare, like the resistor or the sheet resistance of the active regions compare to the well or polysilicon or anything like that? So the active regions typically on the order of tens of ohms. The polysilicon regions typically on the order of hundreds of ohms to thousands of ohms if it's high res poly, right? So generally speaking, the active regions don't really contribute enough noise to worry about. The channel noise is going to be much, much greater than that, okay? The polysilicon gate resistance, however, can be problematic, okay? So if we had a very wide transistor, that means we have a long section of polysilicon, and the longer that section is, the more resistance our gate has, and that can contribute noise to our system. So to analyze what those effects are, we are going to use a distributed model to kind of see what's going on here, right? So I can break any transistor down into this guy right here. I'm going to call RG1, represents some small portion of the gate resistance. And what I'm doing here, I can draw, is making my original transistor look like a whole bunch of smaller transistors connected in parallel, right? So I'm breaking down my wide width transistor into some unit transistors. here's my drain. And down here is my source, all right? And I can say that RG is simply the sum of RG1 plus RG2 all the way out to some RG sub n. This guy should be that n, right? And I can make the number of transistors here as large or as small as I need just by breaking them down into fractionally smaller resistors, okay? So the transistors on the left-hand side of this network see the noise only caused by a small fraction of RG. But over on the right-hand side, they see practically all of RG. So our noise is distributed across this thing. If we were trying to model this as a single lumped resistance, what we should expect to see then is that the lumped resistor in our noise model will actually be less than RG because not all of RG sees all of the noise all of the time, if that makes sense. So we're about to do some math, figure out what that's going to look like, all right? So for our distributed model, where this is our gate terminal, let's say that we have that resistor RG1, and it contributes a noise voltage generator, let's call it VN1. And to make our life slightly easier here, and only slightly, I'm not dealing with the power, I'm dealing with just the noise voltage specifically. And then we would have some resistance here, RG2, which has its own associated noise voltage generator, VN2. This will be at the gate of this transistor. All the way out to some RGN, which has its own associated noise voltage generator, VNN, and every time I write that down, I have to stop myself from drawing a tilde over it so that I'm not dealing with a three-phase RMS neutral voltage, which is what I'm used to from teaching circuits too many darn times. So I apologize in advance if I wind up throwing a tilde over there and make it start looking like an RMS voltage. It's not supposed to be. It's just what my muscle memory forces me to try to do. Here's our drain, and for the sake of our analysis here, we'll tie our source to ground, okay? So what each of these noise voltage generators are going to do is they are going to cause some noise voltage drain current to occur, right? Because this transistor converts voltage at the input to current flowing through the drain at the output. So we'll have some current IN2, like so, and we'll also have a current here, INN, like so. And we can say that our current IN1 is simply GM1 times VN1. IN2 similarly will be GM2 VN2 all the way down to INN, which will be GMN VNN, right? So all of those individual portions of a transistor wind up converting that associated noise voltage into some distributed noise drain current. And if we apply Kirchhoff's current law at the drain node, that's happening there. What we wind up seeing is that IN total, so that would be the current flowing into the drain, simply IN1 plus IN2. And we just add them all up together to get to INN. Everything making sense thus far? All right, so since we can express these drain currents in terms of our noise voltages, we're going to do that. And so this will be GM1 times VN1 plus GM2 times VN2 all the way out to GMN times VNN. All right. So does that make sense? All right. So if we subdivided our original transistor into a bunch of equal sub-transistors, what can we say about the transconductance of each of these sub-pieces? They should all be exactly the same. Absolutely correct. So if GM1 is equal to GM2 is equal to GMN, what I'm going to say is that all of these sub-transconductances is simply the overall transconductance divided by N, the number of units that we broke this thing out into, okay? Which should make perfect sense because all we're doing is changing the width, making it smaller, right? All of the other parameters of our transconductance are going to be exactly equal. VGS, VTH, MUN, COX, even L. The only thing that's changing here is we're making W look smaller and smaller and smaller. So we can simply say that it's the overall transconductance divided by the number of sub-transistors we break this thing up into, okay? So under this case, we can say then that IN total is GM divided by N multiplied by N times VN1 plus N minus 1 times, sorry, this should be VN2. Close menu. All the way out to exactly 1 times VNN. All right. If we assume, and I'm going to have to go to another page here. Assuming VN1 through VNN are uncorrelated, then that means that our power spectral density is GM over N squared multiplied by n squared times Vn1 squared plus n minus 1 squared times Vn2 squared, all the way out to Vnn squared. Okay. Now, similarly to what we did with the transconductance, let's say that since we're breaking this guy up into n identical transistors, we've broken our gate volt, or excuse me, our gate resistance up into n identical resistances, right? So if RG1 is equal to RG2 is equal to RG sub n, then V1, or excuse me, Vn1 squared has to be equal to Vn2 squared has to be equal to Vnn squared. And these will all equal exactly 4 kBT multiplied by Rg divided by n, right? So if they all have the same resistance, then they all generate the same noise voltage spectral density. And I've broken up that whole resistance into n subcomponents. So from here, I can say In squared is Gm over n quantity squared times 4 kBT times Rg over n multiplied by n squared plus n minus 1 squared, and then n minus 2, n minus 3 squared, etc., until I get to 1. And so I have, this would be a algebraic series, is that right? Not a geometric series? It's a series. This is the sum of a series. Let's go there. We're not math majors. So this guy right here can be represented by n times n plus 1 times 2n plus 1 over 6. So if we evaluate this guy as n approaches infinity, then In total becomes Gm squared times 4 kBT times Rg over 3. And from this, our total noise voltage I can get by saying In total divided by my transconductance squared just gives me 4 kBT times Rg over 3. This Rg over 3 term is what's actually used to determine the noise. Okay, so we can see that it winds up being, the noise is generated not by the overall resistance because we can't use a simple lumped parameter model. So we get this guy. So we actually see about a third less of the noise as we would expect to see. It's a lot of math to get to that result. I absolutely understand that. However, that can still be problematic. So the last thing that I want to talk about today is two ways that we can get around this noise or lower the contribution of this noise. And they are both layout techniques. Okay, so if we have our basic transistor, I'm going to draw the basic one first. Here's our active region for our drain. Here is our active region for our source. We see RG. So the first modification that we can do is this guy. All right. So effectively, if we increase the number of contacts, we effectively cut down the contribution of the noise by a factor of 4 because we've halved the contribution of the gate resistance further, right? So it's now in parallel with itself effectively through this configuration, all right? So this is called adding contacts. Our second method, and it's the one that I personally prefer for what it's worth. It's called folding. So in this guy on the left, obviously the poly is our gate. Let's call this guy on top our drain, and this guy on here our source. And we're literally just lowering the resistance because we're forcing that polysilicon to be in, have another parallel path that's effectively nothing connected to it. And so we cut down that overall resistance by a factor of 2, which cuts down the noise by a factor of 4 because it's always based on the resistance squared. Maybe less obvious here. Obviously our polysilicon is our gate. This guy on the outside is our drain. This guy in the middle is our source. This guy on the outside is also the drain. So effectively what we're doing is we're cutting the width in half and distributing it over these two forks so that we use half as much polysilicon to get the same effective width, which gives us half of the resistance and therefore 1/4 of the noise contribution. So they give us the exact same results, both folding and adding contacts. And we can use either or both. Right. All right, I'm 2 minutes over. So what we're going to talk about on Friday is 1/f noise for probably 10 to 15 minutes, and then get into noise analysis of amplifiers and all that kind of good stuff.